In this video, we are going to design the one more problem of cantilever beam. So by using IS 456 2000 codebook rules, so the given problem is a cantilever beam width 300 mm projects 2.5 meter beyond fixed end and carries service load is 15 kilonewton meter. Use M20 concrete and Fe 4 and 5 steel. So this is the given problem. So first step in our RCC, first step is to write on the given data. So that data are, they have given width, that is 300 mm. So I have written here. They have given B is 300 mm. So B is 300 mm and project 2.5 meter beyond fixed end. They have given clear span, that is nothing but clear span, small l is equal to 2.5 meter and carries a service load of 15 kilonewton meter. So that is nothing but live load. They have given 15 kilonewton meter and they said to use the M20 concrete and Fe 4 and 5 steel. That is nothing but our FCK is 20 Newton per mm square and Fy is 4 and 5 Newton mm square. So this is the only data we have in this particular problem. So we'll see step by step. So the first step is to find out the effective depth. So step 1 is to calculation of the effective depth. So for that, as per clause 23.2.1a, page number 37, what it says we'll see. So this is a page number 37, clause number 23.2.1. what they have said: basic values of span to effective depth ratio for spans up to 10 meter. So for cantilever beam they are given 7. So now we are designing the cantilever beam. So they have said our L by D ratio for cantilever beam should not be greater than 7. So the same, I have taken a L by D ratio as 7. So now we are calculating effective depth. So I have rearranged it. So D is equal to L by 7. So D we have got is 2.5 meters, that is nothing but 2500 mm divided by 7. So substitute all the value. Simplify this, we'll get our D value as 350 mm. So this is how we calculate the effective depth. So next step is to assume the effective cover. So now assume the effective cover. So I am taking it as 50 mm. So it is necessary for calculation of the overall depth. So our overall depth is denoted as capital D. So for that we have the formula effective depth plus effective cover. Substitute all the value. Our effective depth value which we have got is 350. So 350 plus we have assumed effective cover as 50 mm. So 50. Substitute all the value. Simplify this. We'll get our overall depth value as 400 mm. So this is how we calculate the effective depth and our overall depth. So now we'll move the next. So step 2 is to find out the effective span, that is denoted as capital L. So for that again, as per clause 22.2 C, page number 35, what it says we'll see. This is the page number 35. For cantilever beam, the effective length of a cantilever shall be taken as its length to the space of the support plus half the effective depth except where it forms the end of a continuous beam, where the length to the center of support shall be taken. So what they have said, to calculation of the effective length for cantilever beam, we should take the clear span plus effective depth, half of the effective depth they have mentioned here. So as per clause 22.2, so our L is equal to clear span plus effective depth divided by 2, half of the effective depth. So substitute all the value. Our clear span they are given is 2.5 plus our effective depth was 350 divided by 2. Substitute all the value. Simplify this, will get our effective span value as 2.6 meter. So this is how we calculate the effective span. So step 3. So step 3 is to calculation of the load. So for that, self weight of the beam we need to calculate. Self weight of the beam formula, we have B into D into rho. D is our overall depth which we have calculated. So B they have given is 300 mm. 300 mm nothing but 0.3 meter. So 0.3 into D is 0.4. Rho is the density of the RCC, that is 25. Substitute all the value. Simplify this, will get our self weight of the beam value as 3 kN per meter. So now they have given the live load, that is 15 kN per meter. So now add its self weight of the beam and live load to find out the total load. To find out the total load, live load plus self weight of the beam. Substitute all the value. After simplifying, we will get our total load value as 18 kN per meter. So next is to calculation of the factored load, that is denoted as WU. For that we have the formula 1.5 into W. W is our total load. So 1.5 into W is 18 we got. So 18, substitute all the value. After simplifying, we will get our factored load value as 27 kN per meter. So this is how load calculation is done. Factored load also called as the ultimate load. So next step is step 4, calculation of the bending moment, maximum bending moment. For cantilever beam we have the formula WU L square divided by 8. So W is ultimate load which we have calculated. That is, substitute all the value. 27 into our L we got is 2.6 divided by 8. By simplifying, we will get our MU value as 91.26 kN meter. So in terms of Newton mm, that is 91.26 into 10 to the power of 6 Newton mm in terms of Newton mm. So step 5, next step 5 is to calculation of the D required. So we need to calculate the D required. So why we need to calculate the D required is because the whatever the effective depth we have provided, that is whether it's sufficient to carry this load or not, we need to check. For that we are calculating the D required. So I will show step by step. So for that calculation of the D required, we have the formula, that is MU limit is equal to 0.138 FCK BD square. For steel 415 we have this formula. So now equate the both formula, MU limit and MU. So by equating these two, we will calculate the D required. So our MU is equal to 0.138 FCK B into D square. So now we are calculating D required, so that I have moved these two here. So D is equal to under root of MU divided by 0.138 FCK into B. So substitute all the value. So our MU value we got was 91.26 into 10 to the power of 6. 0.138 FCK is 20, B is 300 mm. Substitute all the value. So after simplifying, we'll get our D value as 331.99 mm. So to carry this moment, our D required is 331.99. But how much we have provided? So we have provided our D as 350 mm. So our D provided is greater than the D required. So NC, our D required is less than the D provided. Our design is safe because we have provided D as more than it required. So this is how D check is done. So after this, we'll go for the calculation of the MU limit. Step 6 is to calculation of MU limit. For that we have the same formula we are using, which we have used for the D check. Again we are using the same formula here. mu limit is equal to 0.138 FCK BD square. Substitute all the value. 0.138 into our FCK is 20 and B value was 300 and is 350. So by simplifying we'll get our mu limit value as 101.43 kilonewton meter. So in terms of Newton mm, it will be 101.43 into 10 to the power of 6 Newton mm. So our mu value which we have calculated, we got is 91.26 kilonewton meter. So our mu limit value is 101.43 kilonewton meter. Hence our mu limit value is greater than the mu. When our mu limit value is greater than the mu, our section is under reinforced. So we need to design the singly reinforced beam. So for this conclusion we have to find out the mu limit, whether the section is under reinforced or over reinforced to conclude this. If mu limit is less than the mu, our section we need to design the doubly reinforced. When our mu limit is greater than the mu, we need to go for the design of singly reinforced beam. So next step 7 is to calculation of the AST. So by using the formula, AST is equal to 0.5 FCK divided by Fy into 1 minus under root of 1 minus 4.6 mu divided by FCK into B into D square, bracket close, B into D. By using this formula, we have to calculate the AST. Substitute all the values. 0.5, FCK is 20, Fy is 4 and 5. 1 minus under root of 1 minus 4.6, mu value is 91.26 into 10 to the power of 6 divided by 20 into 300 into 350. B is 300 mm and D is 350. So after simplifying, we'll get our AST value as 871.92 mm square. So this is how we calculate the AST. So for calculation of the AST we have two methods. By using quadratic equation method, the formula which is given on your code book on page number 96, by using that formula, and if you don't want to go for the quadratic equation method, by simply remembering this formula you can also calculate the AST. Both the answer will be the same. So now assume the 20 mm pipe bars. To find out the area of each bar, that is denoted as small AST. For area, finding the area of each bar, we have the formula pi by 4 into d square. D square is our diameter, which is 20. Substitute. After simplifying, we'll get area of each bar value as 314.15 mm square. So next we'll go for the calculation of number of bars required to carry this area of steel. So now number of bars. For number of bars we have the formula AST divided by area of each bar. The AST we have got is 871.92. So area of each bar we got is 314.15. Substitute all the value. After simplifying we'll get number of bars as 2.77. So we cannot provide 2.7. So I am making it 3 numbers. So then you can calculate the AST provided. So for that we have the formula number of bars into number of each bars. So number of bars we got is 3. So area of each bar is, we got 314.15. Substitute all the value. After simplifying we'll get our AST provided as 942.45 mm square. So NC provide 3 numbers of 20 mm pi bars at top, that is tension reinforcement. So next is as per clause 26.5.1.1 A and B, That's given on page number 46 and 47. What it says, we'll see. So we need to calculate the AST minimum and AST maximum. Area of reinforcement, minimum reinforcement, area of maximum reinforcement as per clause 26.5.1.1. So we'll see. So this is the page number 46 of clause 26.5.1. 5.1.1 tension reinforcement. Minimum reinforcement. The minimum area of tension reinforcement shall be not less than that given by the formula. That is AST minimum is equal to AST minimum divided by B into D is equal to 0.85 divided by Fy. So what they have said, our AST minimum value should not be less than the value which we when you calculate by using this formula. So there is one more rule. So for maximum reinforcement, the maximum area of tension reinforcement shall not exceed 0.04 B into D. So our area of maximum reinforcement should not be greater than the value when we calculate by using this formula. So we need to apply these two criteria. We'll see one by one. The same formula which is given on page number 46 and 47 I have written here. So AST minimum is equal to AST minimum divided by B into D is equal to 0.87 divided by Fy. So now we are calculating AST minimum. So I have rearranged it. I have moved B and D to here. So that's 0.87 B into D divided by Fy. Substitute all the value. 0.87 our B value is 300 and D value it was 350. So Fy is 4 and 5. After substituting, so by simplifying we'll get our AST minimum value as 215.06 mm square. So our AST maximum formula 0.04 B into D. Substitute all the value. After simplifying we'll get our AST maximum value as 4800 mm square. So what they have mentioned here is our AST minimum our AST value should not be less than 150 and it should not be greater than 4800 mm. So our AST value which we have calculated is how much? That's 871.92 mm square we got. So our AST value lies in between AST minimum and AST maximum. So that's why our AST is greater than the AST minimum. Our design is safe because our value lies in between AST minimum and AST maximum. So our AST, our required AST VM, our AST is greater than the AST minimum. So now we can design the further. So now we have satisfied one more codal rule. So next step is to calculation of shear reinforcement. For that we have the formula for cantilever beam. Shear force formula we have WU. We have VU. It is denoted as VU is equal to WU into L. So substitute all the value. By simplifying we'll get our shear force value as 70.2 kN. So next is calculation of nominal shear stress, that is denoted as tau V. So for that, as per clause 40.1 page number 72, this formula is given on page number 72. So same formula I have written here. Tau is equal to VU divided by B into D. This formula is given on page number 72. So substitute all the value. So after simplifying we'll get our tau V value as 0.66 Newton per mm square. So next we'll go for the calculation of percentage of tension steel reinforcement, that is denoted as PT. For that we have the formula 100 into HT provided divided by B into D. So don't get confused here. Here we need to substitute a